The universe is saturated with things to discover and to know, but there are mysteries so hard to crack that it keeps some physicists awake at night. What if scientists have been wrong about what they have believed to be true for years? There are unknowns with huge implications staring in the face of physicists. Can they ever be able to be known? Number 5. Does the graviton exist? The Standard Model is one of the most accepted theories that we have that attempts to describe and understand certain aspects of our universe. This model describes the world of particle physics by breaking down the types of elementary particles into two main categories of particles. Some particles will be classified as a fermion, which are known to have half integer spin, while others will be classified as bosons that have a whole integer spin. Fermions are particles that make up physical matter, like quarks and electrons, while bosons are the particles that facilitate the interaction of forces and other ways that matter behaves. The electromagnetic force is carried by the photon, the weak force by the W and Z bosons, and the strong force by the different types of gluons. But one fundamental force has yet to have its particle partner identified: gravity. In an attempt to merge quantum mechanics and gravity, physicists introduced a theoretical particle called the graviton that carries the gravitational force. Discovery of a graviton would push physics one step closer to a complete Standard Model and a better understanding of how gravity behaves. Unfortunately, the graviton has never been found, even using the best equipment we have today. Its continuing elusiveness is beginning to worry some scientists who think that they may need to look elsewhere to unlock the mysteries of gravity and finally merge it with the rest of quantum theory. If the graviton can't be found, what will that mean for the Standard Model and of our understanding of forces? Would everything have to be revisited? Number 4. Where our universe's fundamental constants come from? Why do they have the values that they do, and how did they get them? Anyone who has studied physics in grade school has come across fundamental constants that are vital in many of the formulas and theories used to describe our world. We are familiar with the speed of light being constant around 186,000 miles per second. But there are other constants, dimensionless constants, that sit at the very heart of the universe's makeup that have no units associated with them. For instance, the fine structure constant is a constant with a value of 0.007297. But why this number? What is the significance of why does it show up in the equations and laws of physics so often? This particular constant shows up in electromagnetism and actually governs the strength of magnetic interactions. Constants like this one show up everywhere in physics, but no one really knows where they come from. They just appear in the math used to explain our physical world. Could these values be the most basic building blocks of our entire universe? Some scientists think so. A new theory being presented argues that the universe can be fully built on the backs of just 7 fundamental constants. While playing around with the models that simulate the growth of the universe, researchers decided to see what would happen if these constants were different. It turns out that these values are essential to our existence. In nearly every simulation with these constants at different values led to a dead, empty universe. Number 3. Can consciousness be explained with physics? Since the dawn of scientific inquiry thousands of years ago, humans have attempted to understand and explain everything we experience in our reality. Ironically, one of the largest mysteries that has yet to be understood may have been part of every human since the birth of our species. Consciousness. What is consciousness? What allows our brains to process information in the way that it does? What had to change in order for us to gain self-awareness? The advent of modern technology has allowed us to measure and map the brain clearer than ever before, but the mystery of consciousness exists. There have been many who put forward theories as to what consciousness is, some involving forms of religion, different types of spirituality, or even a quantum-level connection to a universe-wide web. The goal of physics is to know our universe and how it functions. There must be a way of understanding how everything works on a physical level if you were to look close enough. Many believe that consciousness must come from physical processes in the brain within the connection of neurons, combined with the electric pulses they communicate with. But even with the capabilities of our instruments today, there has been no definitive evidence as to where these mysterious features of our minds come from. Is the origin and function of consciousness stuck in the realm of unknowability, or will science advance to the point that we will be able to unlock its mysteries? Number 2. Can we fully understand quantum mechanics? It wasn't until the early 1900s that physicists were first introduced into the strange and unintuitive world of the quantum realm. Turns out that as we look further into the ultra-small scales of the universe, it seems to just get weirder and weirder. In the macro world, we can throw a ball and predict where it will end up after a given amount of time. But it's not that easy in the world of the very small. The rules and laws that we have learned govern our reality seem to break down or completely change at the scale of subatomic particles and interactions. One of the greatest American physicists, Richard Feynman, once said that, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Most of us are familiar with the double-slit experiment. If you're not, check out one of our earlier videos diving into the weird phenomenon of quantum superposition. This experiment is a classic example of quantum weirdness. It boils down to the fact that by measuring and observing which slit the particle went through, the researchers caused the particles being fired at the slits to behave differently. Instead of acting as a wave of potentials moving through both slits, the wave function collapses and the particles act like a small marble and only travel through one slit. Are our interactions with the world required for particles to exist as a physical particle rather than a wave of probability? Physicists have thus far been able to understand some of the earlier conundrums that plagued the original founders of quantum physics, but there are still vast areas of quantum world that remain a complete mystery. Will we ever be able to understand quantum interactions fully, or are there simply parts of it that can never be understood? Number 1. Can all the fundamental forces be unified into one? Within our universe, there are 4 fundamental forces that dictate every single interaction that occurs. The 4 forces, electromagnetism, gravity, the strong nuclear force, and the weak nuclear force, or the weak interaction, exist throughout our universe, holding everything we know together. For the most part, we only notice our interactions with the 2 forces that have strong effects on the macroscopic world, electromagnetism and gravity, in our everyday lives. The strong and weak nuclear forces only work on the very small scale, holding quarks and particles together in order to form atoms. But new experiments taking place in the Large Hadron Collider have shown physicists that these forces may not be separate after all. There have already been tests that have shown the electromagnetic force and the weak nuclear force unifying into a single force. The results also hint that the same unification should happen with the strong nuclear force at high enough energy levels. But just because the theories say they should happen doesn't mean that it will. Nature does not always listen to what the leading theories have to say about it, and no particular accelerator in existence is powerful enough to reach the energy levels necessary for the strong force to unify with electromagnetism and the weak interaction. And that still leaves out gravity. Could the gravitational force be unified to the other 3 in this same way? Remember that gravity is the only force that we have yet to find a corresponding boson for. If the graviton doesn't exist, it may mean that gravity is wholly different from the other forces and requires a different type of understanding. A large part of the community continues to believe that the forces must fit together in some way and are expanding on their theoretical and experimental models. Are we one step closer to forming a unified theory of all the forces, or will science be disappointed with a never-ending hunt for an impossible solution? Thanks for watching. Leave us a comment down below and let us know if there are any mysteries that keep you up at night. See you next time on Matter.